each example, you'll be fine. Just follow the process. Greetings and welcome, friend. Have you ever wondered if you've been hit by a car? Maybe. Well, today you can find out whether or not you've ever been hit by a car. Perhaps, if you knew the vector parametric equation representing your path and the path of the vehicle, even though those two paths might have intersected, it doesn't necessarily mean you got hit by the car, though. Because if you both didn't inhabit that region at the same time, you didn't get hit, right? Like I walked across the street when I came to school this morning, and some of you drove across the same street that I walked across, but I don't think any of you hit me. Why? Because we weren't there at the same time. So today we're going to introduce a variable, not only knowing like the paths of objects, but we're going to have a variable that represents time, so we'll be able to describe the location that a point or an object is at a particular time. So we're going to be able to describe movement. All right. So we're talking about vector and parametric equations. And for starters, I've got this vector equation of a line. It says a line through point 1 parallel to the vector A is defined by the set of points, point 1, point 2, such that for some vector it is equal to a scalar multiplied by A. All right, for some real number t. Therefore, this is true. This left-hand side, by the way, you've seen that before. That's just the way you found a vector between 2 points, right? x2 minus x1 and y2 minus y1. So the vector that passes between those 2 points is going to be some scalar multiple of the vector A, since it was parallel to vector A. So kind of like the idea of this sketch going on here. Imagine I've got like point 1 and point 2, and here's my line that passes between them. All right, and then vector A would have been some parallel vector. All right, so this would have been vector A. So this would have been like A1 and A2 or something like that, right? So some scalar multiple of A, if I have t times A, all right, I'll end up getting the same vector that it is from P to P2. All right, they might not have been the same length to begin with, but multiplying by some value of t will account for that. So this t, like I said, will later on use to represent time. So instead of just having direction and distance, I can actually have how long it took for me to travel that far, or where I was at a particular time. So if, say, I was, working for the Star Wars program for the government, trying to intercept a missile with my own ballistic missile, right? I'd want to not only be able to have my missile's trajectory intercept the other missile's trajectory, but for both of those missiles to be there at the same time, right? So time is important, right? Right. So let's do a little example of this. Star Wars as a movie was also an initiative by the government to create ballistic missiles that can intercept nuclear missiles from Russia. Yeah, I think, something like that. Maybe. Who knows? So that would be like the intersection of a parabola and a straight line. There you go. So write a vector equation describing a line passing through this point parallel to this vector. Now, the way we'll do this is we'll let any point on the line be x comma y. All right, so that way I can represent any point on the line, not just a single one of them. And so what I would end up doing, we'll label these. This will be my x2, y2. This will be my x1, y1, and this will be my a1, a2. And all I'm going to do is just kind of plug it into this formula here, like so. So I'll end up having x2 minus x1, so that's going to be x minus 1, comma, y2 minus y1, so that's y minus 4. All right. So there's my vector that passes between my any point and my given point, and that's going to equal some scalar t multiplied by vector a, 3, negative 2. And this is all I had to do. I just kind of plugged them in the appropriate slots. Yeah, so this actually, if I pick a particular value for t, I will find an x and y that is on that line. So if t is 0, if t is 10, if t is 0.7, if t is pi, it will give me a different point on the line that is parallel to this vector that passed through this point. All right, so I would have to like pick values for t, which hopefully we'll be able to do by the end of the video. Now, this next part I'm not going to have you write down, but I'll explain it. If I want to derive the parametric equation of a line, all right, here is my vector equation of a line, right? So what I've done here is I've taken the x coordinate of each of these and set them equal to each other. All right, you don't have to write this part down. So x minus x1 would equal t times a1, right? Because multiplying a vector by a scalar, you just distribute. So that's what I would have there. And if I wanted to solve that for x, I could add x1 to both sides, and that's what I would end up getting. And then I did the same thing for the y's. I said y minus y1 is equal to t times a2, right? Which is what I had. And then to solve that for y, I just added y1 to both sides. So this is actually going to be two separate equations representing a parametric, all right, a parametric set of equations of a line. So this is parametric equations of a line. Yeah, this you write down. And parametric, the t variable is literally called our parameter. So I might even make a note of that. T is called a parameter. So these are called parametric equations because my location is based off of an additional little piece of input is what's going on. Yeah, for this case, we're going to use a parallel vector to help us out. So we use the direction of that vector as kind of as our cue. And so this is all for linear movement or motion. Tomorrow we'll actually talk about parabolic or different behaviors you could get. But essentially what this ends up representing is this is the horizontal location. And the y equation gives you your vertical location. All right. So our x equation is just telling me where am I horizontally speaking at any given time. The y equation is where am I vertically at any given time. And I can find my location using them in conjunction with one another. So, and the variable t was literally called t because of time. That was the main reason this type of math had been discovered. Although I suppose maybe you could come up with some sort of parametric equation based off of another variable input. But usually it's just time. So, let's do an example of this. Nope. Or no, that is what it was. Aha. But you don't have to write all that down. We'll just write So I'm looking for the parametric equation according to vector q passing through this point. Let's see. So what I'm going to do is label what I've got. So let's see. So this would here's vector q. So this is going to be my a1 and a2. Here's my point. So this will be my x1, y1. And all I'm going to do to write my equation is to plug these values in. So I'll have x equals x1, which is -2, plus t times 3, or I'll just write that as 3t. And then the y equation starts at a location of -4 and will be moving down 2 units for every time t. T seconds, t minutes, t eons, whatever we decide t was. So those would be my equations. And if I wanted to graph this line, you could actually make a table of values. It would be like a triple value situation where I'd figure out t, I'd figure out x, I'd figure out y. So let's say I'm interested, where's t, where's the point at -1 second or year or whatever, 0, 1, and 2. And let's think about this. So if t is -1, all right, 3 times -1 is -3 plus -2, I would get an x value of -5. If t is 0, 3 times 0 is 0, -2 plus 0 is 0. Or sorry, -2, my bad. And this plus 3t means for every 1 second, I'm increasing 3x units. So -2 plus another 3 is 1. 1 plus another 3 is 4. And you could see that if I actually plugged in like 2 for t, 3 times 2 is 6. 6 plus -2 is 4. So it does verify and work that way. And also this kind of behaves a little bit like a y equals mx plus b in the sense that this is going to be my starting value whenever t is 0. Right? So at time 0, -2 times 0 is 0. And so that's just going to be -4 is the location of y at time 0. At time 1, it will be 2 less than that, so -6. And at time 2, it'll be 2 less than that, so -8. But yeah, it's just a matter of kind of plugging it in or figuring out a pattern. And you can graph it once we have all these points. So if I plug in -1 for time, that'd be +2, -4 plus 2 is -2. So if I want to graph this now, let's say I'm at the point -5, -2. This is where I am at t equals -1. Then I'm at the point -2, -4. Right, so here I am at t equals 0. Then I'm at the point 1, -6, so over 1, down 6. Here's at t equals 1. And then I'm at the point over 4, down 8 at t equals 2. All right, so I can plot all of those points. And so this is the line. All right, this represents the path that the object is on, but it is not at all of those points at all times. All right, so it's moving along this path, right? Its location changes depending on what time it is. So that path is just the trajectory of the object, all right, like a bullet fired or, right, a car moving or an airplane flying through the sky. But this additional parameter time allows me to know where it is at what time. And I believe you might notice the distance between these points. This is going down 2 and over 3, which notice are the y and x coordinates of my parallel vertex. Right, because this is the vertex 3, -2 would have been right here. So notice that in 1 second it was traveling down 2 and over 3, down 2 and over 3 repeatedly. So that's the equation of a line based on that. So let me show you one last example. This one's going to be a quick one. Yeah, it's not that bad. Last example we'll do today. So let's say I have an equation of the line and I want to make a parametric equation, or a set of parametric equations that represent it. All right, so here's the equation of a line. That's like the path of the object, but I want to introduce a variable t of my own, just to represent the location of my object at time t. So the first thing we do is let's just let x equal t. All right, so I just arbitrarily decided that on my own. So my first equation is x equals t. My second equation will come as a result of plugging in t for x. So y equals -4 times t plus 7. Or that could simplify to be y equals -4t plus 7. So this would then be kind of my set of parametric equations where I've just introduced my own t. Now, if I was actually trying to model something right in the physical space, I could have changed what t was equal to. I could have said let x equal 2t or half t or whatever it is, and I could have then plugged it in. I still would have had equations that represented the same path, but the location of the object would have been different depending. Or I think I actually can even do something like let x equal t minus 1, and I could have plugged it in and simplified and done things like that. So anyways, so thanks for watching, Internet friends. Have a great day. Bye-bye.